This is tutorial on rate of reaction part 1 by SCA Charles AB on with reference Cambridge International AS by Laurie Ryan and Roger Norris. Hello, this tutorial is on rate of reaction. With the learning outcome you are going to have, you should know how to explain and use the term rate of reaction, activation energy, including reference to Boltzmann's distribution. You have catalysis. Explain the qualitatively how the following affect the rate of a chemical reaction: concentration, temperature, catalyst, and explain how catalyst can be homogeneous or heterogeneous, and describe enzymes as biological catalysts. So this is the rate of reaction part 1. So now, rate of reaction. So we need to know that the rate is just defined as the amount of reactant or product divided by time, but usually we define the rate as a negative of the reactant the reactant divided by time, or positive for product divided by time. So this is what we define as rate. And now we need to know that the reaction kinetics mostly occur due to the collision theory, and that collision theory usually occur because of the degree of dispersion of an atom, which can be seen from the entropy of a reaction, as we're going to see in entropy and free energy later. So we need to know that collision theory needs to know that atoms are going to vibrate and are going to move in different directions. So since they move in this different direction, they are capable of colliding with each other, and they are capable of reacting to produce at different rates. So now, in order to have the rate of reaction, we need to know that the rate formula, as we're going to see in the rate kinetics part 2, rate formula is going to be given as a certain constant, which is a rate constant, times the concentration of the reactants. So that's the rate formula. So rate formula is actually a constant times the concentration of the reactant. So now the point to put in mind, so when you have so rate is actually negative k the concentration of the reactant, depends on if it is first, second, or third order. So now when you have that k, it varying with respect to three main factors. The first factor which can vary the equilibrium the rate constant is the frequency of collision. The frequency of collision is a factor z. The next one is the orientation of collision. We have frequency of collision, we have orientation of collision, and we have the vibration of the particles. So these are the three main things. Factor p is the orientation of collision, factor f is the frequency of collision, and factor z is the vibration of the collision. So now f is given as a, which is the Arrhenius constant, is given as a e raised to the power negative ea all over rt, where ea is actually activation energy all over r, which is the molar gas constant times the temperature. So that's the final formula for the k. So from here we can see that it can vary. The collision theory states that you can vary the rate of reaction due to the frequency of collision, which is the factor f. We have the frequency of vibration, which is the factor z, and we have the orientation of the molecules. So in this case, like this example, the molecules are not well oriented, so there is no reaction. Why? In this case there is energy, and you see that in this case the molecules are well oriented, so there is reaction. So these are the different points to put in mind. So now, effect of concentration on rate of reaction. We have different things. So again, apart from the equilibrium constant, where we have the frequency which will vary with respect to three factors, that is frequency of collision, which we have frequency of vibration, and we also have the orientation. We also have other factors which can cause the change in rate of reaction. So these factors are: number one, we have temperature. Temperature can be seen inside the formula of frequency of collision, where we said that its frequency of collision is going to be which is small e raised to the power negative ea all over rt, where e is activation energy, t is a temperature. So we have the concentration. Concentration can have effects on rate of reaction. If you increase the concentration of the substance, it's going to increase the probability for the molecules to contact to each other, and that increased probability increases the rate of the reaction. The temperature, if you increase the temperature, you are going to increase the frequency of collision, increase the frequency of vibration. So since you increase that frequency of collision and frequency of vibration, more particles are going to react. So the rate of reaction is has increased. And this could be seen inside the Boltzmann distribution curve. And the Boltzmann distribution curve say that what at temperature T theta you have this distribution, but when you increase the temperature by 10 degrees Celsius you have this distribution. So you see that what the first case where you have temperature T, the activation energy is actually the energy. So this is the Maxwell-Boltzmann distribution is actually the number of molecules attain a certain energy against the molecular energy. So we see that in this distribution you have less molecules which have energy above the activation energy, while when you increase the temperature by 10 degrees Celsius, more molecules have activation energy and can increase by 2 times. So you need to know that the rate of reaction can increase by 2 times when you increase the temperature by only 10 degrees Celsius according to Maxwell-Boltzmann distribution. So now the next point is catalysis. So what's the catalyst? The catalyst is a chemical substance which is going to increase the rate of reaction by reducing activation energy but remains unchanged at the end of the reaction. So that's a catalyst, and it functions by providing an alternate route to the chemical reaction with a lower activation energy. So we have two main types of catalysts. You can have homogeneous catalyst, you have heterogeneous catalyst. Homogeneous catalyst is one that has the same texture as a solid or as a mixture in which it is placed. Example, when you have let's say hydrogen peroxide and you have the heterogeneous catalyst. So in this case, it's an example of heterogeneous catalyst. In this heterogeneous catalyst, hydrogen peroxide decomposition usually occur at room temperature and pressure, but usually slowly. But when you place a catalyst of manganese oxide, which is a solid, in this, manganese oxide is actually having different chemical state as the mixture. So in this case, you are going to say that it is a heterogeneous catalyst. So, and a homogeneous catalyst is one that has the same chemical state as a mixture in which it is placed. So we have the next one, the enzymes. The enzymes, actually you need to know that these are biological catalysts which are much more specific because they have an active they have an active site which is specific to the different reactants which are being involved. So we have the enzyme substrate complex. So we have enzyme for the substrate, form the enzyme substrate complex. It provides a lower activation energy and it produces enzyme product. You need to know that enzyme and enzymes are very specific catalysts, and they are more efficient than inorganic catalysts. They increase the reaction rate by 10 raised to the power 6 to 10 raised to the power 12. The enzymes are very specific. As a consequence, specificity, the enzymes do not produce byproduct. Also, we have enzyme work very mild condition, for example 35 degrees Celsius, pH 7, atmospheric pressure and atmospheric pressure. So these are the low condition in which enzyme can work. You can have an example of an enzyme which is urease in order to break down urea and water to produce ammonia and carbon dioxide, urease. So from here we can say the reaction kinetics part 1 is over, and say thanks for your kind attention. Please don't forget to like and subscribe for the channel. Thank you.